Hello, yeah, I'm Peter Robbins from the Centre for Applied Marine Science in Bangor University, and my colleagues on this work were Simon Neal, who's here today, and Matt Lewis, who are both also at Bangor University. And the main aim of this work was to try to quantify the natural variability in sedimentary processes at a particular site, and use that as a measure of the impact of tidal energy extraction at that site. So this is our case study, a region off the northwest coast of Anglesey in the Irish Sea. And this is one of 7 regions of interest around the UK for first generation tidal energy extraction. And the Skerries Channel, which is in between the mainland Anglesey and a small group of islands, has been leased by the Crown Estate by Siemens and MCT. And that's likely to be one of the first tidal-stream arrays in the world. The Crown Estate have also released a demonstration zone just to the southwest of that site, just off Holy Island of Anglesey. And there are other companies looking are interested in the area as well, like Minesto and Open Hydro. So why is the site good for tidal energy extraction? Well, it's got quite high tidal velocities, greater than 2.5 meters per second. Water depths are optimal for tidal stream arrays, 30 odd meters. It's close to shore, 5 kilometers or less, where there is a harbour that's got space and is willing to work in this industry. And there's also good grid connection. So it's all set up well from that respect. In terms of sedimentary processes in the area, it's quite interesting. There's 3 main processes that are going on. There's high tidal dissipation causing high suspended sediment concentrations and the turbidity maxima. In terms of bedload transport, there is the formation of sandbanks and beaches in and around the area. And then there's the general shelf scale sediment transport, where there's a strong net flow into Liverpool Bay past this area. The model system that we have been using is the Telemac modelling system. It comes in with 3 modules, a hydrodynamic module, a wave module and a sediment transport module that we run on a high-performance computer called High Performance Computing Wales. It's one of the 200 top computers in Wales, in the world. But we've only just started using Tomawac. For this work, we actually used the Swan wave model system. So this is my grid for the whole of the Irish Sea, extending from the Celtic Sea up to Scotland, and there's the region of interest in the middle, Anglesey. This is just a little video showing the model resolution around Anglesey over a spring neap tidal cycle. So you can see the unstructured mesh varies from 5 kilometres offshore to increases to 1 kilometre around all the coasts, and then increases further to 200 metres around Anglesey, and then further still to around the tidal energy array of individual device-sized resolution. So you can see lots of closely packed arrows signifying the resolution, and we're going through a spring tide at the moment, so lots of yellows and reds and oranges. And you can see the areas where the tidal currents are strongest through the Skerries Channel up there in the north and around the north of the Skerries Islands, and then also off Holy Island to the southwest. That's where the demonstration zone is, and the top one's where MC2 site is. And you can see in the middle of those two regions there's an area of low tidal velocities where sediment accumulates. You can see much less velocities during the neap tide. So some analysis of the model showing peak tidal currents from M2 and S2 constituents. You can see this is the same plot repeated twice, just I've moved the contour line showing on the left areas above 1.75 meters per second, on the right above 2 meters per second. So you can, if you take into account that the Bristol Channel is often too shallow or too tidal, you can see that this is one of the most favourable high energy sites in the RSC. You can also pick up all these other sites, potential sites. So I'll talk about the sediment processes that we've observed and modelled in the area. First of all is the suspended sediment concentrations. So high tidal dissipation generates high suspended sediment concentrations, and the formation year-round of the Anglesey turbidity maximum. The turbidity maximum enhances nutrient supply for marine species, it increases secondary production, and serves as a nursery ground for marine species. We used our, at Bangor we've got a research vessel called the Prince Maddock, 40-foot long research vessel, kitted out with all the instruments and a crew. And through various projects like the Low Carbon Research Institute and CCAMS, we've been out in the area and collected sediment and suspended sediment samples, which have been used to validate the sediment transport module. And you can see here that looking at suspended sediment concentrations in the RSC, this is the region where there's the highest turbidity maximum, so it's ecologically really important. And this is where the array will be. This is where sediment samples were collected, and this is some qualitative model validation at that site. Second process is bed load transport and the formation of sandbanks. So we've got strong tidal flow through here and bedrock on the bed, and then we've also got strong tidal flow here. But in the middle we've got this kind of eddy circulation system and low velocities in the middle and sediment accumulation. So we used the multi-beam on the boat to sample the sandbank. And I'll just say the importance of sandbanks is to protect the coast from storm events and refract and dissipate wave energy. So it's a good idea to know how they form and how they move and what their variability is and how that will be affected by any energy reduction. So we then went back and did a larger survey of the sandbank using multi-beam. Lovely data showing all the wave-driven and tide-driven ripples on the sandbanks. And there's a comparison of the two different surveys that were 6 months apart, showing some natural variability. So our aim then is to try and use the model to further quantify this variability. I set up the model with the sediment size class equivalent to the sediment of the sandbank that we saw, with an initial flattened bathymetry around the sandbank, and then after a month of simulation, roughly where the sandbank is, a sediment accumulated at roughly the same volume as the sandbank. The model wasn't high enough resolution to resolve the individual dune features, but it did predict the formation sandbank, and then it kind of levelled off at that kind of 5 minutes. Okay. So the third process is the shelf scale sediment transport, and the area has been shown in previous studies to be a sediment conduit for material into Liverpool Bay, and I modelled the bed shear stress of the region and showed comparable results to previous studies about the net and total bed shear stress through the area. So now the next step is to look at the natural variability in all these processes, and we used the variability in the net bed shear stress to do this. So this is the using the SWAN spectral wave model of the Northwest European Shelf at 1/24th resolution. The details of that are in Simon and Reyes' paper. And you can see over a 7-year simulation that there is interannual variability in the bed shear stress at the site and at the sandbank position, and then there is intra-seasonal variability, more stress in the winter than in the summer. So we use the stress calculations from the SWAN model and combine them with the tidally induced stress from the Telemac model, using Salisbury's total stress formula to come up with the overall stress per month over each year and over the 7-year period to come up with the natural variability. And then the final step was to simulate tidal energy extraction at the site. So this is the tidal energy array. I modelled rated power extraction of 10, 50, 100, 300 and 500 megawatts. So these are kind of first generation tidal energy farms, and these are future maximum or beyond maximum tidal energy farms. And the final kind of result we came up with was that okay, if you look here, that is the annual or the winter mean bed shear stress at the tidal energy site, and the grey areas above and below are the natural variability in the system over the winters. So if you read, and then once you start taking energy out, the bed shear stress is reduced at the site. So at what point does taking energy out of the system exceed the level of natural variability? Well, it's this rated figure of 165 megawatts. So that's for winter. The same plot, that's that plot. Same plot again for summer, shows that there's less variability, so you need less energy extraction, 85 megawatts, to exceed natural variability. But we use less, in the UK we use less energy in the summer, so that kind of makes the kind of overall impact similar. And you can see further afield over the sandbank, the impact of the energy extraction on the bed shear stress is much less, so it's never really going to exceed natural levels of variability. So I suppose that's quite a positive result for the energy extraction industry, but just to be aware, this is just one site, it's just the kind of process that should go on in environmental impact assessments to each site. Yeah, thanks. Oh, well, conclusions. Yeah, the model did well at reproducing all the sediment processes. First generation arrays are likely to be insignificantly affect the sedimentary natural variability in sediment processes. But yeah, this kind of method should be used in other sites. Okay, thanks.
Thank you very much, Peter.